Cheering, like, what is going on right now?
Too many in-jokes and memes for me to keep
Yeah.
track of. At some point, somebody will release a script like they did for Rocky Horror for the audience participation, and everybody will know all the jokes. Okay. I want to think about change of variable as a transformation. So when I think of polar coordinates, I really think of taking my x and y coordinates and turning them into r and theta with the equations I have, r equals square root of x squared plus y squared when I only restrict myself to positive ones, and tangent of theta is y over x. I can think of this transformation as taking in two variables and spitting out two variables. Wait a minute. That's just like a function, right? Our functions f of x, y, z, or f of x, y, take in two variables and spit out one. What if I took in two variables and spit out two variables? I could think of it as a function like a transformation whose domain is two variables and whose output is two variables. And then I could think of t as a transformation from x and y to r and theta. So there's just a new way to think about a change of variables. Same thing if I think about spherical. That would be a transformation that takes three inputs in and gives out three outputs. Now, what's nice about these particular transformations is that I already know the equations for x, y, and z here, right? But that means that getting the other ones are a little harder. Up there, I wrote the equation as if you put in x, y, z, and you get out rho theta phi. But those equations put in rho theta phi and get out x, y, z. So this is the other way. This is it's kind of like going like an inverse. Well, it isn't really an inverse unless we have some nice properties. I do want to make an important note here. These functions, as written, may or may not be continuous. These functions up here are not continuous on the entire domain. Because if you put in and take a derivative here, what's the derivative of the square root of x squared plus y squared? Well, partial with respect to x, partial with respect to y, right? If I do that, then I end up with x over the square root of x squared plus y squared. That's not continuous at zero. If I do the partial with respect to y, it's not continuous at zero. The inverse tangent is not continuous in a whole bunch of places. So as written, these are not continuous. But these are continuous as written. And I like transformations that have continuous things in them. I'm going to use those. And I'll use the same language I used before, and I'll call these C1 transformations if the first partial derivatives are continuous. So those equations for the x, y, and z out of spherical, those are continuous. Their derivatives are continuous. Whether I'm taking that derivative with respect to rho or phi or theta, those have continuous first partial derivatives. Whereas in the other direction, they're not. I like thinking of two-dimensional transformations a little bit better than three-dimensional because I can draw two-dimensional transformations better. So I think of a transformation from two-dimensional space to two-dimensional space as having two inputs, two outputs. This is garbage up here. So I have a UV plane. My transformation spits out an XY plane. And if I have a point over here, U1, V1, then over here, I'll have a point X1, Y1, and that's the image in the right side from the pre-image in the left side. If I'm being really precise about this, we talk about the domain and the codomain. And then the set of points that we hit is the range. So if I had a set over here, I could get some other set over here. And then R would be the image of S. So far, so good. I stick my points into one equation. I get out another pair. I get out a point. So this, we can think of this as like moving stuff. Like a zoom or a pinch, right? Or a rotate. Or even something more complicated. Those of you that have taken linear algebra, matrix transformations are exactly like this. They're just special subcategories. We're looking at more general transformations. Questions? We'll do some more examples. We'll do some more discussion. I need one other specific piece of information. What does it mean for a function to be one-to-one? Exactly. No two points land on the same thing. No two pre-images have the same image. Or each pre-image has a unique image. If the outputs are the same, then the inputs had to be the same. Not all transformations are one-to-one. Polar coordinates is a perfect example of this. This X and Y can have multiple different sets of polar coordinates that all hit it, right? We could use a positive R, we could use the opposite angle and then use a negative R. There are lots of different ways to get to a point. So whether or not my transformation is one-to-one only matters in a couple of cases. But the case in question here, the reason I want to mention this is that if my transformation is 1-to-1, then it has an inverse. P raised to the -1 power. Inverting my transformation is a nice thing, but not all transformations have inverses. I'm going to want to use ones that do sometimes, and then sometimes I'm just not going to care. Ready for an example? Here is a transformation. Put in u and v, we get out u squared minus v squared and 2uv. What the hell? I would like to see what the effects of this transformation are. So I'm going to pick a region in the UV plane. I'm going to look at the unit square, S. And my question to you is that when I do this transformation, what happens to that square? Where does this square go in the XY plane? I'd like to draw a picture. How am I supposed to do that? Advantage number one. Look at this transformation. Is it C1? Now, another way to write this transformation is to write x equals u squared minus v squared and y equals 2uv. And then in the xy plane, those are my coordinates. But I can think of the partial derivatives. What's the derivative of x with respect to u? And the derivative with respect to v? And those are continuous everywhere, aren't they? They're polynomials. Same thing down here in y, the derivative of y with respect to u is 2v, and the derivative of y with respect to v is 2u. Those are also continuous everywhere. So this is a C1 transformation. And when it's continuous, stuff stays together. So that domain S, that set, that blob, is going to move over to the XY plane and still be a single blob. It's going to stay connected. That is a preserved characteristic, an invariant. Things that are connected in one space end up connected in the other. You can't rip something apart using continuous functions. So, if I figure out where the edges of this thing go, you can tell me what the edges are over here, and we can draw the picture. So, I'm going to number the edges starting here on the u-axis as side 1, side 2, side 3, and side 4. And this should look as familiar as all When we did our extremes, absolute maximums and minimums, we had to check the edges of our region. I'm going to do the same idea here. I'm going to figure out what happens to this piece side one. So let me think about side one. What do I know about all the points in side one? Look carefully. Their V value is 0. And if V is 0, then T of UV becomes T of U0. What happens then? Well, I put in V equals 0 to those points up there, right? And I get U squared minus 0. And 2U times 0, well, that's always 0. What do I know about the values of U on this side? On side one. I actually have a boundary. U is always between 0 and 1. Because I'm on this piece of the square. And U is stuck between 0 and 1 there. Okay, wait a minute. If I put in 0, where do I go? If I put in 1, the image of this side is here. That's T of side 1. Now, it doesn't quite move in the same way, because as we go from 0 to 1 here, by the time we get to a half, we've only gotten to a quarter. By the time we get to 3/4, we've only gotten to 9/16. So we move at different speed as we go from 0 to 1 on the left versus the right. But I can say, oh, this little stick is going to go to this little stick. Let's look at side 2. What do I know about side 2? About all the points on side 2? U equals 1. But then I should know something about V as well, right? What do I know about V on that piece? So now I'm going to do T of UV, but that's going to be T of 1 comma V. What do I get here? Plug that in up here. If U is always equal to 1, then U squared is 1. And I get 1 minus V squared. And if U is 1, I get 2 times 1 times V. I get 2V. I get a set of parametric equations. X equals 1 minus V squared. Y equals 2V for 0 less than or equal to V less than or equal to 1. How do I know what that looks like? So I can draw it over there on my picture on the right. I don't have the foggiest idea what this looks like. But I have a graphing device that'll graph parametric equations, right? The graphing calculator. Mode. Parametric. Y equals, oh, I got other stuff still stuck in there. Let me get rid of that. 1 minus t squared and 2t. Now I go to my window and I want t to go from 0 to 1. And then I can draw this picture. I'm going to set up a small window because I don't think these are going to get very big. Because remember, y is always going to be less than 2. And x is going to start at 1 and then get smaller. So when I graph this, I see this shape. Oh, you can't see squat there. Now I could ask what shape that is. It kind of looks like part of a parabola to me. So let's check. I go back to my parametric equations and I'm going to do the elimination of parameter. I'm going to say, oh, look, I can take this equation and I can write v equals y over 2. And then when I put that into the other one, I get x equals 1 minus y over 2 quantity squared, or 1 minus y squared over 4. That is a parabola. It's a parabola that opens to the left, which is exactly part of what I drew, isn't it? Hot darn. Do side 3 for me. On side 3, I'm up here. So I know that v is always equal to 1. And I know u is between 0 and 1. So I can do the same setup. T of uv becomes T of u1. And then I get u squared minus v squared. And 2 times u times v, which is 1. Those look very similar, don't they? X equals u squared minus 1. Y equals 2u. All I have to do in my graph is change that first equation to be t squared minus 1. Now I'm going to run into a problem when I graph this. Problem is that u is between 0 and 1, right? What happens when you plug in 0? And my window only went from 0 to 5. I need to fix my window. I'm going to change this so that instead of going from 0 to 5, I go from negative 2.5 to 2.5. Now I've centered the y-axis. Ah, it's the mirror image, isn't it? So now I have this. Any guesses on where side 4 is? Yeah. With a little bit of work, you can show that this is T of S4. Now, here's my overarching issue. If I wanted you to do the integral of some function on this region, because remember, this is my R, the image of my square. If I asked you to do the integral on that region R, you would need to have the parabola for this side and the parabola for that side. And if you did this as a type 1 region, you'd have to go from negative 1 to 0, parabola minus line, and then from 0 to 1, parabola minus line. If you did this as type 2, you'd have to go from parabola to parabola, and then from 0 to 2. Those both suck. Whereas if I was over there in the square, I'd be ready for 0 to 1 and 0 to 1. And that would be a much easier setup, wouldn't it? If I was integrating over here, it would be much easier than integrating over here. And what I have in front of me is a transformation that takes one shape to the other. Right here. These equations start in U and V and give me X and Y. If I could measure the distortion from here to here, then I could integrate over here instead and just adjust dA. Somewhere over here, if I think of a little bitty box with du and dv, somewhere over here, there's an image of that little bitty box. Right? But it's not a box anymore because our boxes became curved, right? So if I know how much this changes, then I can account for that change. And I can use it to integrate over there instead. The distortion created by a transformation is called the Jacobian of that transformation. Now, most Jacobians are usually given like J as a symbol. But that doesn't tell me where we're going and what we're coming from and all that other stuff. I need to have a transformation, in our case, from 2 dimensions to 2 dimensions. And if I write X is some function of u and v, and y is some function of u and v, and those are continuous, a C1 transformation, then the Jacobian measures the change in the area. Hey, wait a minute. Wait a minute. I've done this before. How did we do the area for a parallelogram? Way back in chapter 12, a long time ago. How did we find the area of a parallelogram if we knew the sides of that parallelogram? Cross product. Cross product was a determinant, wasn't it? I, J, K, and then the vectors, right? The Jacobian is a determinant whose entries are partial derivatives. Now, I don't just like calling this J because that doesn't tell me what I came from and what I went to. We also write this as the double partial. It's the partial of X and Y with respect to U and V. And then if we want to integrate, we take the absolute value of this. If I want to do the double integral on the ugly region, I can go back to the nice region if I switch to U and V and multiply by the absolute value of my Jacobian. Then down here, I would, instead of writing dA, I would write du dv. Or dv du, whichever is easier. All of a sudden, my change in coordinates has to have some adjustment to its length, and its adjustment to its length is exactly the length of the cross product made up of the change of variables. Now this looks like I am talking out my ass. Ready? My favorite, most practical example. Those are continuous functions. They take me from x and y to r and theta. I would like the Jacobian here. So what I need you to do is I need you to take some derivatives. Notice the order up here. X and Y are on the top. That means X and Y give me the rows. X row, Y row. U and V are on the bottom. So I get the U column and the V column. So Here, I'm going to get an X row and a Y row. I'm going to get an R column and a theta column. So I need the derivative of X with respect to R. What is X with respect to R? Partial derivative time. There's your equation. It's derivative with respect to R. What's your derivative with respect to theta? Now look at Y. Y with respect to R. Y with respect to theta. Now do the determinant, AD minus BC. But wait a minute. Cosine times cosine, I get R cosine squared theta. Minus a minus becomes a plus. I get R sine squared. Wait a minute. What's that? I almost. Just R. Which means, according to that integration idea, when I want to do an integral, dx dy, but I'm better off thinking in polar, I have to stick something before dr d theta. What do I have to put there? I have to put an R there. R dr d theta. Where did the R come from? Right here. I didn't make it up. Jacob did, but I didn't. And this accounts for the distortion as I go out in that little bitty polar wedge that we were looking at. Now I don't have to try and justify this geometrically. I have a purely calculus derivation of this. The transformation we were working on. T of uv is u squared minus v squared, and then 2uv. What's the Jacobian of this transformation? with respect to u of x is 2u. With respect to v, it's minus 2v. Y with respect to u is 2v. Y with respect to v is 2u. When I do my cross for the determinant, I get 4u squared minus negative 4v squared. That's never negative. Since that's never negative, I don't have to worry about the absolute value. But that means if I wanted to do the integral of something, anything, on, where's my picture? If I wanted to do an integral on this, I could instead do an integral on this. And all I would have to do is put that in front of du dv. Figuring out what the transformation should be is hard. Here on page 1058, in example 3, we have this picture. I want to integrate on this thing. If I try and do this as a type 1 region, I'm okay here because I have a line on top and a line on the bottom. But over here, it's horizontal on top and a line on bottom. If I want to do this as a type 2 region, again, I have to cut it at some point. That's nasty. But look at the edges. The diagonal lines are both x minus y. So what if I made that one of my variables? U equals x minus y. I need another variable. So I look at what other equation might come into handy, and they actually gave it to me, x plus y and x minus y. And when I do that, this is my new region. And that is a perfect type 2 region, isn't it? It's bounded on the left and the right by diagonal lines, the top and bottom by horizontal, by number. And the Jacobian for this transformation is a constant. This is a linear transformation. Its Jacobian is a constant. And the example of actually doing the integral is down here. Questions? Cylindrical coordinates, right? R, dr, d theta, dz. Where's the r come from? Well, now I have 3 equations, right? My 3 equations in 3 variables, if my transformation goes from R3 to R3, then I will have a Jacobian like that. We'll have 3 on top and 3 on bottom, which means I get a 3 by 3 determinant. And I do this just like I did the cross product. I go across the top row or I go down the first column. I make my life easy. Which means if I go back to the very beginning of today's discussion, I put up polar coordinates and I put up another transformation. What was the other transformation I put up? Oh, come on, y'all took notes. I watched you do it. And that's spherical, isn't it? So instead of UVW, I have rho, theta, and phi. And it's got to be in this order, because that's the way I wrote the coordinate system down. Regardless of where they show up in here, it's this order for my partial derivatives, which means I can do the Jacobian of this. So let's set it up. I'm not going to do it. I just want to set up the Jacobian. Three rows, three columns. The rows are X, Y, Z. The columns are rho, theta, phi. So I'm going to go down columns instead of across rows. That means I need X rho, the derivative of X with respect to rho. Yeah, but what is that derivative? No, that's exactly what I want. X rho, Y rho, Z rho, X theta, X phi, Y theta, Y phi, Z theta, Z phi. But now I need to actually put those things in. So what is X rho? And the derivative of Y with respect to rho is sine phi sine theta. And the derivative of Z with respect to rho is cosine phi. Now I got to do my derivatives in theta. X theta. What's the derivative of cosine theta? So I get rho sine phi sine theta with a negative sign. The derivative of Y, the derivative of sine theta, rho sine phi cosine theta. But Z is rho cosine phi. What's the derivative with respect to theta? When I do the phi derivatives, the derivative of sine phi is cosine phi. So I get rho cosine phi cosine theta. Then I get rho cosine phi sine theta. The derivative of cosine is minus sine, minus rho sine phi. That's my Jacobian for spherical coordinates. After you're done trying not to barf, there's a lot of algebra involved in working this out, and a lot of trig identities, and a lot of factoring, right? I don't want to do this. Fortunately for you, it's on page 1059. Please take a look at where I end up. I promised you I didn't pull it out of my ass on Friday. There it is. Rho squared sine phi d rho d theta d phi. It works. The absolute best part of all of this is I only have to do this once. Once I've done this once for coordinate systems I use a lot of, this is enough. Every time I'm going to do spherical coordinates, I'm going to stick a rho squared sine phi in there because I've done this Jacobian transformation. If I can remember that, I don't have to do it every time. This finishes chapter 15. Wednesday's question and answer day. What's that make Friday? Exam 3. The review sheet is posted. You get another index card. Wednesday's question and answer session. Bring me all the questions you've got. I will see you then. Have a wonderful rest of your day.